For chapter 25, which is taking electricity and magnetism and sort of looking at them from two different perspectives, two different sides of a coin, really. It's going to turn out that a changing magnetic field will produce an electric field. Changing electric field produces a magnetic field. That in turn produces electromagnetic waves. So this chapter is all about electromagnetic induction, inducing an electric field from a magnetic field and vice versa, and then electromagnetic waves. So that's a consequence of having changing electric fields, changing magnetic fields. Okay, so we're going to try to understand the nature of electromagnetic induction and later in the chapter, waves. Okay, so these are the same picture just being seen by two different two different things, bees versus humans. Bees have a different range of vision than humans. So bees can see all the way into the ultraviolet, but they don't really have much in the orange and red, whereas humans go all the way from red to violet. So we would see things differently. So this is part of the electromagnetic spectrum. This is just the visible part. There's a lot more to the spectrum than this, but this is the visible part. So usually when you hear the word light, you think of things that you can see. But there's some light that we can't see. For example, ultraviolet, infrared, microwaves, radio. You can't see those with your eyes. Part of the spectrum you can see with your eyes is just the visible part, and it's kind of a small part here. Okay, so and it also turns out that the way that you look at this, there's going to be an energy dependence on this. So here we're actually going from lower energy up to higher energy, and then even higher than this would be things like gamma rays. So we'll talk about that a little bit in this chapter, and then also when we go back to chapter 28. Okay, so maybe you've seen these driving to West Lafayette, windmills. All of a sudden they just appear on the horizon, very quiet, very large. So essentially what's happening with these windmills is the wind is turning the turbine and we're producing electricity. So we're going to have a conductor moving in a magnetic field. The angle between the conductor and the magnetic field changes, and when that happens, we produce electricity. So in the previous chapter we had motors. We supplied the electricity and we got things to turn. So a generator is just the opposite of that. You supply the motion and you produce electricity. Okay, so there's definitely the connection between electricity and magnetism. One can lead to the other and vice versa. So a physician programs a pacemaker by inducing a rapidly changing magnetic field. So a rapidly changing magnetic field induces a voltage in the implanted device. You might have used this on a smaller scale. If you have wireless charging on your phone or your toothbrush or something like that, you're using this idea. There's a changing magnetic field going through a loop of wire somewhere that's inducing current to flow, and then you can charge up a device that way. So something called electromagnetic induction. Pretty cool stuff, really magical. Later in the chapter we can look at electromagnetic waves. So electromagnetic waves have an electrical part and a magnetic part, and we'll see this, and they're equal to each other in magnitude. They depending on which units you use, they have the same amount of energy. The electrical part and magnetic part are perpendicular to each other, and then they travel through space. They don't need anything to travel through. We talked about waves in Physics 220. We had like water waves, for example, or waves on a string. You actually had to have something, some media for the wave to propagate through. Electromagnetic waves, you don't. They just go through through a vacuum, through empty space. Okay, good. So we'll talk about those in this chapter as well. So induced currents. So we now know that a current can create a magnetic field. That was from the previous chapter. We had the long straight wire, the loop, the solenoid. Can a magnetic field create a current? And it turns out it can. It has to be a changing magnetic field. So Michael Faraday experimented with two coils of wire wrapped around an iron ring in an attempt to generate a magnetic field. So here's a battery, here's a switch, we've got some wire going around an iron ring here, and there's a voltmeter here. So essentially what happened is you close this ring, there's no magnetic field here, you close it, current flows, and then you do produce a magnetic field. And while it's going from nothing to something, current is generated here. So while the magnetic field is changing, you can induce a current over here. So it's got to be a changing magnetic field. Once it reaches its final value, then there's nothing. It's just while it's changing that you have a induced current. Okay, so what I've done is open up that Faraday's FET from the notes. So here I have a bar magnet, and here's a loop of wire. So this, as you can see, this magnet definitely has a magnetic field associated with it, but this light bulb's not lighting up. So what you can do is take the magnet, move it closer. See, while it's moving it lit up. Move it back out, move it closer, back. So when I move it closer, the magnetic field strength is getting greater through the magnet. So this actually lights up. It doesn't really matter how much the strength is, it matters how fast it's changing. So if you change this really fast, you can get this to go really bright. For some reason the graphics aren't working so great, but that's the idea. The faster you move this, the faster the magnetic field is changing, the bigger the induced voltage. And then when it's just sitting here, nothing happens. You have to have a changing magnetic field. And that's what's happening. The strength of it's changing as I get closer and farther away. So the key for electricity is to get something to change the magnetic field for you. You could put a squirrel on some kind of treadmill, power the changing magnetic field that way. If you have a loop of wire close by, you could get you can generate some electricity. I could turn on this. This is kind of hydroelectric power. So when I do that, this water's going to flow, hit here, the magnet's going to turn. So the magnetic field that's going through this loop is going to be changing, and a changing magnetic field produces electricity. If you're ever stuck on a desert island somewhere, maybe you could come up with something like this. So while it's changing, and I'm opening up this so it's changing faster and faster, while it's changing, while the magnetic field is changing, let's see, let me actually show the field. See, as the north goes one way, then the south goes here. The magnetic field through this loop is changing. When that happens, you can produce electricity. So on a much larger scale, at NIPSCO or wherever you get your electricity from, there's something going on here. There's got to be some angle between the magnetic field and the loop, or the strength of the magnetic field going through here, that changes, that produces electricity. Okay, it's more complicated than this. As you see, it's getting brighter and dimmer. There's something called three-phase, where this happens kind of one right after the next, and you can keep this thing, keep it brighter. Okay, so that's the idea. Changing magnetic field through a loop generates electricity. Okay, let's go back to the notes. Okay, so that was Faraday's idea. Close the switch, the magnetic field goes from nothing to something, and while that happens, you have current, and then when it stabilizes, then there is no current again. So it's just not the fact that there's a magnetic field, changing magnetic field. So Faraday's experiment did not generate a steady current. It's only while it was when the switch was being closed and we got up to the steady state current. So again, changing is the key here. The rate of change is really important. The faster it changes, the bigger the induced EMF. So here's some experiments. Faraday placed one coil directly above another without the iron ring. So remember, this is a battery. You close this shape here is going to produce a magnetic field. The magnetic field that's produced by the upper one is going to go through the lower loop here and generate some electricity. So there was no current in the lower circuit while the switch was in the open position, but just when you close it, when the current goes from nothing to something, during that period of time, while the magnetic field through here then goes from nothing to something, we generate electricity. Okay, here's another experiment Faraday did. Push the bar magnet into a coil of wire. This action caused a momentary deflection of the needle in the meter. So just like you saw in the FET, when you move this one way, move it back, you induce an EMF. Moving it in was one direction, moving it back out was another direction. And the faster you do it, the bigger the EMF you produce. Okay, so Faraday connected a momentary current by rapidly pulling a coil out of a magnetic field. So taking the actual coil, moving it this way, moving it that way. You change the magnetic field strength through the loop here, and while that's happening, you produce electricity. Okay, so Faraday found that there is a current in a coil of wire if and only if the magnetic field passing through the coil is changing. Okay, and that's while it's changing, you induce an EMF. Okay, this is called electromagnetic induction. It's the idea behind generators. So motional EMF is the voltage produced by the motion of a conductor in a magnetic field. So we kind of have an idea about this from the previous chapter. If you take this iron bar, and it's a conductor, it doesn't have to be iron, it's a conductor, you move it to the right, there's a magnetic field on a magnetic field into the page, so there's a magnetic force on a positive charge to this side, leaving this side negatively charged, and you can set up a potential difference that way. Okay, so the magnetic force is QVB, that's from the previous chapter. You set up an electric field back the other way, and again you get to the point where the electric field part, which force part, which will be pointing down on a positive charge, is equal to the magnetic force part pointing up. Okay, so the faster you pull this, the bigger the voltage you are going to induce. Okay, so there's the electric field part, which is equal to QE. You get to the point where those are equal to each other. QE is equal to QVB. This looks just kind of like the velocity selector that we talked about before. Okay, so you can solve then, the Q's cancel out, E is equal to VB when you do this. So this V is the speed. And we also know that you could look at the voltage here. Delta V is equal to E times D, so you could plug that in. Let me actually write that down. 10. Okay, so delta V is equal to ED, so delta V over D is equal to E. And you can take that and plug it in here for E if you want to, and this is the D I'm talking about, the width of this. Okay, so this is the voltage. That's what you could actually directly measure. So you can figure out how much voltage is generated. So as you pull this conductor through a magnetic field, you produce a voltage. Now imagine if this was like the wings of a plane going through the Earth's magnetic field, right? You would develop a voltage across the tips of the airplane wings. Something in the millivolt range. You'd have to take that into consideration if you were designing the electronics of the airplane, because you would really develop a voltage just across the wings of the airplane. Same thing happens in your car, just you're not going nearly as fast, so the voltage is not as much. Okay, so I use D here for the thickness. The book uses L. So here's the voltage that's developed across a conductor moving in a magnetic field. So the voltage is the speed times the length times the magnetic field strength. Okay, and the homework problems from this chapter, I'm making a separate video for those this time. I did not do that in the previous chapter for homework 5, but I will do that for this chapter. Okay. Okay, so there's two ways to generate EMF. This is the old way that we've talked about before. This is a battery where through chemical processes you separate charge from each other. Here's another way of doing it. Take a conductor, move it through a magnetic field, and let the magnetic force separate the charges. It turns out the faster and faster you pull this, the more and more voltage you develop, the harder and harder it is to actually pull this thing through the magnetic field. So you don't get anything for free with this. You still have to put the energy in to move it. Okay, so here's an example. Boeing 747, wingspan 65 meters, cruising at 260 meters per second over northern Canada, where the magnetic field is 5 times 10 to the 5th, directed straight down. Okay, so what is the potential difference between the tips? So we're assuming here that the plane is perpendicular to the magnetic field. The magnetic field is straight down, the plane is going this way. V and B are perpendicular to each other. So we want to know what is the potential difference developed across the wingtips. So we just came up with the formula for that. Conductor moving through a magnetic field will get this motional EMF. Oh, so this is quite a bit actually. 260 meters per second, wingtip 65, Earth's magnetic field 5 to the minus 5th Teslas. Put it all together and you get 0.85 volts. So quite a bit. You'd have to take that into consideration. Okay, so let's take a look at the units. We end up with volts somehow from meters squared times meters per second times meters times Teslas. How does that give us volts? So let's take a look at the units we have here. So meters per second times a meter, that would be meters squared. Go to pen. So on the top here we have meters squared per second times Teslas. How does that become a volt? So I did this on the other day in a video for, I think it was the March 1st video. Remember what a Tesla is? Tesla is a Newton per amp meter. So let's see if we could put that in for Tesla, see if that cleans anything up here. So then this would become meters squared over seconds, and then Teslas would be newtons per amp meter. Okay, so remember what a volt is, first of all. It's a joule per coulomb. So if we could make this thing in the bottom into a joule per coulomb, we would be in good shape. And it looks like we can. One of these meters cancel out. Oops. So at the top I have a Newton meter, which is a joule. And then at the bottom I have a second times an amp. So an amp is a coulomb per second. So I have a second times coulomb per second. So the seconds cancel out. And then I have a joule per coulomb, which is a volt. Okay, so it is correct. That's the little key there that kind of takes us from the magnetic world back to the electrical world. Okay, good. So 0.85 volts developed across the wings. So a moving conductor could have an EMF, but it could not sustain a current because the charge has nowhere to go. So you'd have to actually connect it somewhere. So you got to be careful though with an airplane that you didn't accidentally connect one side to the next. Okay, good. So here's another way of doing this. You could actually pull this to the right. You develop a voltage across this bar, and then you could have current flow. So this side's positive, this side's negative. It's acting like a battery, and you're pulling it that way. Okay, so remember, you have to put the force on it this way to get it to. This is the force from you, that direction. But now there's current moving through this. There's a magnetic field, so there's going to be a force on this conductor from the previous chapter, ILB. Okay, so the current is up, the magnetic field's into the page, there's a magnetic force back this way. So as you pull it to the right, there's a magnetic force back to the left. So you don't get anything for free. And the more you pull it, the bigger the current, the bigger the current, the bigger the magnetic force. So you could do this, you just, again, won't get anything for free. The harder you pull it, the harder the magnetic force is back the other way. Okay, good. So in a circuit, the charges that are pushed towards the end of a moving conductor can continue to flow around the circuit, as you saw in the picture. The moving wire acts like a battery, as I said, and then you could actually figure out the amount of current. This is from Ohm's law. But now we know this EMF is V times B times L, and again that's the velocity, little v. Okay, good. So you get to these are equal to each other. Whatever you're pulling, the magnetic force goes back the other way, as I showed you. So this is the magnetic force, I times L times B. It's also equal to the EMF divided by R. That's what this part is. And then we still have an LB there. So it turns out to be the velocity, length squared, B squared divided by R when you put it all together. Okay? So take that, multiply this by this, and you get this more complicated looking part. And again, this homework question, I'll do a separate homework video for the Chapter 6 homework questions. Or homework 6, not from Chapter 6, from Chapter 25. Okay, good. So you pull one way, the magnetic force is back the other way. So once you get it going, I mean, it looks like they're equal to each other, but maybe you already have it moving, so you've induced something to flow. Okay, good. Because there is current, power is dissipated in the resistance of the rail. Some problems actually have a resistor built in to the circuit there. Okay, so the work that you do goes into heating up the circuit elements, maybe powering a light bulb or something. So again, the key is, you could do this, or you could get something to do it for you, like a waterfall. Get something to move, generate current that way. Okay, so let's just look and see what the power looks like for this. So this goes back to Physics 220. This is chapter 10 actually. The power is the force times the speed. If you want to look at just the units from this, force is newtons, and then velocity is meters per second. So this would give you joules per second. That's what power is. It's a watt, a joule per second. Okay, so we've seen this from today. That's the pull force. Multiply it by the speed. This is the power then, right? So this is the force, this whole thing here. Multiply it by V, and you get that relationship for power. Okay, no intuition whatsoever with this formula. It just comes by from putting everything together. Okay, so the power that you put in is equal to the power that's dissipated then, just like we have here. So those are equal to each other. Okay, you don't get anything for free, but actually, good thing you can light up the light bulb. So a generator is a device that converts mechanical energy to electrical energy. Lots of different ways of doing this. Again, the key is to get something moving, a conductor moving in a magnetic field, and generate electricity that way. Okay, hopefully we'll see some better pictures of this. Something like this actually. So in this picture, somehow this is rotating. There's a magnetic field, so a current is induced. And then there's something called commutators down here. See, the thing is, the force on the top, for example, is back this way. So if you get something rotating one direction, once you get to the other point, it wants to flip back the other way. This ring won't keep going. So the commutators down here actually change the direction that this thing is moving. That's what these are for. If you notice, when it flips around one direction, a different part of this will be in contact with the other one. These are brushes, so sometimes with generators you have to change the brushes. The brushes are just there to make contact. Okay, and then you could actually produce a voltage that looks like this. Otherwise, the ring would just, this loop here would go one way and then flip back the other way. It wouldn't keep moving. Okay, so it's just a mechanical way of getting this thing to keep flipping over. So as the coil in the generator rotates, the sense of the EMF changes, giving a sine wave, as you saw in the picture there. This is actually called AC current. Okay, maybe you have one of these at home. Turning the crank on the generator flashlight rotates a coil of wire in a magnetic field of a permanent magnet. I have one. You're basically charging up a capacitor, and it's got an LED so that it'll stay on for quite a while. The energy won't be used up too quickly. Okay, so really that's what you're doing. You're your own generator when you do this. You're turning chemical energy in your muscles into some sort of mechanical energy to move this loop of wire in a magnetic field. There's magnets in there, and produce electricity that way. Or really, you store it in a capacitor, and then once you press the button, you utilize it. Okay, there's this idea of magnetic flux. This is a way for us to calculate how much EMF we're actually producing. So Faraday found that a current was induced when the amount of magnetic field passing through the coil changes. There's got to be some kind of changing amount. There's three ways you can change it, and we'll see that, this idea of flux. You have to have a changing magnetic flux. Okay? So we can think about the amount of magnetic flux passing through a loop in the same way you think about the amount of air that blows through this this loop. Or maybe how you have a bucket and it's raining outside. How much water can you collect in the bucket? If rain is coming straight down, you have the bucket like this and you collect all of it. Now, if the bucket's at some kind of angle, you don't collect all of it, so the magnetic flux would be not as great. If you've got the bucket completely with the opening not able to collect any rain, you're not collecting any of the amount, so the magnetic flux there would be 0. So it's a maximum when you're collecting all of the water. It's a minimum when you're collecting none of it. Just like in this picture, when the loop is completely perpendicular, you're getting all of the air. When it's at some angle, you're only getting a fraction of the air. It depends on the angle between the flow of the air and the surface area of the loop. Okay, that's a side view, maximum, and not as much. Okay, so if you consider the front end view of a fan blowing, if you're the fan looking, what are you actually seeing? This is when it's completely upright. This is when it's turned at some kind of angle. Okay, so the magnetic field passing through a loop is also affected by tipping of the loop. So if you have a magnetic field going this way, here's a loop, that's where it's going all the way through, but if you have some angle, then you're not collecting it all. So there's an effective area. It turns out to be a cosine of theta, and theta is the angle between whatever is coming through it and the area. So the area vector is measured perpendicular to the plane of the loop. Okay, so here's a side view of a loop. This is defined as the area vector, perpendicular to the loop. I'll have to use my pen. Here's the loop again. Here's the area vector of the loop. So the formula says, you know, the angle the effective area. This would be a cosine of theta. So it's the angle between B and A. Okay? So it's weird to think of an area vector. So if this is a loop, the area vector is perpendicular to the plane that the loop is in. If that makes any sense there. That's a pretty good picture, I think. Okay? So if you've got a circle here, the area vector perpendicular. It's just a way to tell how much flux you're getting. So when the area vector, here's the area vector, is lined up with the magnetic field, that's when you have the maximum flux. And then when you're at some angle, then you have a smaller amount. Okay, good. So here's the length. This side is A, this side is B. The area vector and whatever's going through it are lined up. So the effective area is just A times B. Now when it's tipped at some kind of angle, you saw from the previous slide, that side was just B cosine theta. So the effective area is AB cosine theta. This little b it's maybe a bad choice of variables. This b is not magnetic field. They're just calling that side length little b. Okay, so finally, the magnetic flux, phi, is the effective area times b. So the effective area is area times the angle between A and B. Okay, so the unit of this, Tesla times meter squared, called a Weber. So if you want to generate electricity, you have to have a changing magnetic flux. So either you have to change the area of the loop, the magnetic field strength going through the loop, or the angle between A and B. You'd have to change one of those. So again, let me just show you this. Here is the loop. This is the area vector. Now, if you have, I'm going to change this to a different color. If you have an external magnetic field, so that's what this B is here. So here the angle between A and B is 0. They're actually lined up with each other. Now if you had the loop laying flat like this, here's the area vector. It's just defined to be perpendicular to the plane of the loop. And you had B, I'm giving you the extreme examples, and you had B this way, here the angle is 90 degrees. And there is no magnetic flux there. Okay? Good. So it's a made-up quantity, magnetic flux. It's just going to help us to calculate the induced EMF. So you're going to have to change A, the actual area, B, the actual magnetic field strength, or the angle between A and B. Those are 3 ways to change the magnetic flux and induce an EMF. Okay, so theta is the angle between the magnetic field and the axis of the loop, or I call it the area vector. Okay. So which loop has a larger magnetic flux through it? So this field is twice as strong. The square is twice as wide. Okay. So loop B. Remember, it's the it says let's see, twice as wide. That means the area is much bigger, right? Just because the side's twice as big, then that means that the area is 4 times as big. Okay. Like, so if this is L over 2, this side would be L. So this area would be L squared. This area would be L squared over 4. Okay. So this one has a greater area. Okay? Good. So it's not how big the side is, it's how big the area is. Okay, the metal loop is being pulled through a uniform magnetic field. Is the magnetic flux changing? It's not changing. As you move to the right, as long as it stays completely in the magnetic field strength is not changing. Now, if you happen to leave the magnetic field, then the magnetic field strength gets less, and then the flux would be changing. So currently, no. The metal loop is rotating in a uniform magnetic field. Is the flux changing? It is. As you rotate this, less and less magnetic field lines go through this. When the loop is completely flat, there is nothing, and then once it starts rotating more again, then you get more and more. Right now it's a maximum, then it goes to 0, then it goes back to a maximum. So yes, you have a changing magnetic flux. Really, it's because the area vector and B are changing. The angle between A and B are changing here. Okay. Let's see. At a particular location, the Earth's magnetic field is 50 microteslas, tipped at an angle of 60 degrees below the horizontal. Okay. A 10 centimeter diameter circular loop of wire sits flat on a table. What is the magnetic flux? Okay. Not sure what that's for. Let's see. Let me read it again. 50 microteslas. Okay. Tipped at an angle of 60 degrees below the horizontal. Okay, so we could imagine what that looks like. A 10 centimeter diameter loop of wire rests flat on a table. What is the magnetic flux? Now, the magnetic flux is not changing. They're not saying how much is the induced EMF. We just want to know how much the magnetic flux is. So A, B, and then the cosine of the angle between A and B. Be careful, they give us an angle here. We'll have to see if this is the angle that we need for the formula. Okay, so here's kind of here's the view of this loop. Here's the 60 degrees between the this one here. 60 degrees, that's what the Earth's magnetic field is tilted at that point, 60 degrees from the horizontal. And then we want to calculate the amount of magnetic flux. We need the angle between the area vector and B. So the area vector is the same as the axis of the loop. It's straight down. B is here. So in our formula, we actually need theta to be 30. That's the angle between A and B, the area vector and B. Okay? It's a circular loop, so don't forget the area of a loop, pi r squared. Okay? So we have that. B is actually given in the problem. We can put it all together. AB cosine theta, here's the area, magnetic field strength, and here's the angle between A and B. Here's the loop. B is here. This is the area vector. This is the 60 degrees they give you in the problem, but we actually need 30 degrees. That's the angle between area vector and B, between the axis of the loop and the magnetic field. Okay, great. Lenz's law. So Lenz's law will tell us the direction that the induced EMF the current's going to flow. So we need kind of a right-hand rule of this. So the German physicist Heinrich Lenz developed a rule for determining the direction of current called Lenz's law. I'm going to read it, but then I'm going to show you how it actually works. There is an induced current in a loop in a closed conducting loop if and only if its magnetic flux is changing. And then here's the key part. The direction of the induced current is such that the induced magnetic field opposes the change in the flux. So let me give you my take on this. Okay, so let's pretend we have a loop sitting there, and there's a magnetic field going through the loop, so you're looking down on it. And later on, so this means initial, later on we have it's increased for whatever reason. Maybe you've taken a bar magnet and you've moved it closer. Take the north side of a magnet and move it closer. So you go from 4 in to 3 in. Now what Lenz's law says is the direction of the induced current is going to be such that we go back, or we tend to go back to this situation. So there is a changing magnetic field, so there definitely is going to be an induced EMF. The question is, which way is the current going to flow? So let me do this one. Change colors here. Now the current is going to flow in such a way that its own magnetic field tries to get us back to the initial situation. So it's going to flow this way. Its own magnetic field, put your thumb in the direction of the current, inside the loop, its own magnetic field, that's why the red color, would be this way, trying to kill off the increase. So if you have a loop, magnetic field strength gets greater through the loop, as I'm looking at it here, the induced current is going to flow counterclockwise. Its own magnetic field, going back to the first right-hand rule, is going to flow clockwise, and then inside its loop, its own magnetic field would be out at us, trying to kill off the increase. Okay, so the black arrows are an external magnetic field. The red dots are the magnetic field associated with the induced current. Let's do a couple more. Actually, maybe I'll just use this picture and erase what I have here. Okay. Okay, so let's go from different color. Let's go from okay, we start out with 4. This is just to illustrate the point, and now we're going to go down to 1. So this would be a case if you had the north side of a magnet and you pulled it away. Nature likes to be in this initial situation, so the induced current is going to flow in such a way that its magnetic field tries to get us back to that initial situation. You could almost guess, because this is the opposite of what we just did. Its current's going to flow clockwise, flowing clockwise, so then its magnetic field would be into the page, trying to get us back to where we started. Nature likes to be in that initial situation, so if we have a decrease, the current's going to flow clockwise so that we try to preserve the initial situation. And you can go through all of these. Let's do another one here. I'll just erase this. Maybe you go from this, and now you have this. So it's into the page, and now it's later on, it's out of the page, out at you. Nature still likes to be in this initial situation. So the current is going to flow like this to try to get us back there. Not only does it have to kill off that increase, it really has to do something like that to get us back. And then the 4 dots and the 4 X's go away, and we're left with 4 X's. Okay? One more. Okay, we're at 2, and now we're at 2. So what does nature do? In this case, nothing. There's no change. There is a magnetic field, but it's not changing. I could put as many as I want here. I could put, let's say I got 9, 6, 7, 8. So that's a lot. That's a big magnetic field strength. But it hasn't changed, so nothing happens. Okay. So there's several situations. You can go through them all if you want to, but that's the idea. Nature likes to be in one situation, so the induced current is going to flow in such a way that its own magnetic field, I should say, tries to get us back to that situation. Okay, let's continue. Okay, so that's my take on Lenz's law. So Lenz's law, the magnetic flux can change in one of three ways, as you can see from the formula. Either the area changes, the magnetic field changes, or the angle between A and B changes. Okay, and that's the only way. If it doesn't change, if one of those doesn't change, you do not induce an EMF. No current flows. Okay, so let's see, magnet at rest, and we bring let's see, magnet at rest creates a magnetic flux down. There is no current. Now, when you moving the magnet down increases the flux through the coil, and you actually get an induced current. This is really the first one that we looked at. If you're from the perspective of looking down, switch this to pen. So this would be something like, when you're looking down on this, just to illustrate this, the magnetic field out of the north through the loop. So you move it down, you increase the amount of current flowing, or sorry, the amount of magnetic field lines. So the induced current is going to flow this way. Its own magnetic field is out at you, trying to kill off that increase. So the induced current then is flowing like I showed you in the red there. Now when you move it away, it's just the opposite. Just like I think that was the second one that I did. You move it away, you get less magnetic field lines going through the loop. The induced current is going to flow clockwise to try to keep us in that situation. Okay? So determines the direction of the applied, determine the direction of the applied magnetic field. The field must pass through the loop. Determine how the flux is changing, increasing, decreasing, or staying the same. So Lenz's law, there's no formula for this. It's just going through and figuring out which direction the induced current is going to flow through the loop. Okay, so let's see what we have here. A magnetic field goes through a loop of wire at the right. If the magnetic field is increasing, what can you say about the current? Okay, so we went through all those actually, the first examples that we did. Okay, so there's the answer. Increasing, it would be B, counterclockwise, trying to kill off the increase. Number 2, decreasing clockwise to try to get us back to where we start. Constant, nothing happens. Okay, so what happens here actually? Example. A loop is moving towards a current wire as shown. As the loop is moving, is there a clockwise current around the loop, counterclockwise, or no current? So as this drops, remember this current is flowing to the left. It has a magnetic field. And then I'm going to have as many here. And then I'm even going to have less here. The farther and farther you are away from this current that's flowing, the less and less the magnetic field strength is. So as this loop drops towards the wire, the magnetic flux actually increases. It would be something like, just to reference this, initially there's 2. As you get closer, I'm just going to say 3. So initially we were like this when you're farther away. And again, I'm just doing 2 and 3 to make it get more. So which way is current going to flow? Okay, well you got a 50-50 chance. If it flows clockwise inside the loop, its own magnetic field would be into page. That would actually make it worse. So it's going to have to flow counterclockwise. And then its own magnetic field would be out at us, killing off that increase. So as this loop drops towards the other wire, we have counterclockwise flow. Okay, as it says here, this is probably a better explanation of what I've just said. Okay, and anyway, as the wire gets close, the loop gets closer to the wire, the flux increases. Nature doesn't want it to increase, so its own current is going to flow in such a way to try to kill off that increase. Okay, excellent. So that, again, that's a synopsis of what I've said. Okay, a long conductor carrying a current runs next to a loop of wire. The current in the wire varies as shown in the graph. Which segment of the graph corresponds to the largest induced current in the loop? Okay, so here's the U0I over 2 pi r. That's the magnetic field because of a long straight wire. It produces a magnetic field which depends on the current. So really we're asking here, which one of these segments is the current changing the fastest? Right, that's where it changes the fastest. It goes from whatever this value is down to this value in a short amount of time, because we got I versus T. Segment C, nothing actually happens. There is no change in current. There's no change in magnetic field. Okay, so E would be the biggest change in current, which corresponds to the biggest change in magnetic field. That will give you the biggest induced EMF. Okay. So Faraday's law, finally. Induced EMF is the EMF associated with a changing magnetic flux, as you can see here. The direction is determined by Lenz's law, and this takes some practice. You could literally go through all the different scenarios, and it wouldn't take you that long, really. I mean, going from something to something greater, in from less to greater, out, you know, that sort of thing, and work them all out ahead of time if you wanted to. And then the size of the induced EMF comes from Faraday's law, and that's what you see here. So this induced EMF, it's the changing magnetic flux divided by the amount of time. A more useful way of maybe looking at this is something's got to change. Either A, B, or the angle between A and B has to change in the amount of time. Now they all three don't have to change, just one of them. So something has to change, either A, B, or the angle between it, and you'll induce an EMF that goes around in a circle. How is it different from a battery? Well, a battery doesn't go around in a circle. This EMF is induced in a circle. It's what makes the current flow. Okay, so when you see that, actually it's the absolute value, one of those has to change. Okay? Now if you have more than one loop, don't forget to write the N here. They all work together. It's like having N amount of batteries in series. Okay, so there are two fundamentally different ways to change the magnetic flux through a loop. The loop can move or expand or rotate, or the magnetic field can change. So you could literally take the loop and shrink it, make it bigger, move it in and out, or change the magnetic field. It's whatever's easier to manufacture from a technological standpoint. Okay, here's a little example here. The following figure shows a 10 centimeter loop in 3 different magnetic fields. The loop's resistance is 0.1 ohms. For each situation, determine the magnitude and direction of the induced EMF. Okay, so let's take a look at that. The first one is the magnetic field is out at us and it's increasing. The second one is it's in and decreasing at the same rate. And the third one, there is actually no magnetic flux. We have a side view of the loop. No magnetic field is going through here. The flux here is 0. It's not changing because none of it's actually going through the loop. So this one, there is no induced current. No magnetic field goes through there, and also even though it's changing, none of it's going through there to begin with, so no current is induced. Now the magnitude for both A and B is going to be the same. Okay, the part that's changing is the magnetic field. Okay, so the current that we're going to have, induced voltage divided by the resistance. So one thing has to change. It's not the area. The cosine of the angle between A and B in either of those is 0, right? And then the cosine of 0, cosine of 0 is equal to 1. Area vector, perpendicular to the loop. Magnetic field, perpendicular to the loop. There is no angle between here. Here's where you actually get the maximum flux. Okay, and then so the A part's not changing. I'm just writing it there. It's the changing magnetic field part. Delta B over delta T. Okay. And then don't forget the R. Okay, so it's a circular loop. Here's the area. They give you the diameter, but don't forget we need pi r squared. So I'm not going to get a number for it for this one, but here's how to do it. Pi r squared for the area. Be careful with the units. This would be 0.1 meters. That's the diameter. So the radius, half that. So you have the area, you have the rate that the magnetic field's changing. That's what this is, 0.5 teslas per second. And they actually give you the resistance too. Okay, so you have to put that all together. Either of those, it's the same thing. It's the same magnitude. We'll have to figure out the direction though for each of those. Okay, so I need to clear up a little space here. Get rid of this. Go back to this. So this one's increasing. So I'm just showing it increasing, going from 4 to 8. So nature likes to be like this. We're going to have to kill off that increase, right? You went from 4 to 8, for example. So to kill off the increase, we're either going to have current that flows counterclockwise or clockwise. Let's try counterclockwise first. So if current were flowing this way, its magnetic field would be out at us. That's not killing it off. That's actually making it worse. So we'd have to have this one flow this direction. And then its own magnetic field would be into the page, killing off the increase. Okay, so clockwise. The second one, I need to make some more room too. This one is decreasing. So let me do my 2 circles. So for example, decreasing would be like going from 4 to 2. Initial, final. Okay, so let's try clockwise. Clockwise, thumb in this direction, its external magnetic field would be into the page. So that's what we actually need. We need to build back to where we started. So this one would be this direction, trying to get us back to where we started. So it's the same thing. Increasing out at you is the same as decreasing in. Okay. So same magnitude of current and same direction of current actually for A and B. All right, let's look at the next one. So here's kind of a neat thing that happens. This is happens with mechanical braking actually. There are 2 loops lying entirely in a metal sheet between 2 magnets, as you can see there. As the sheet is pulled, the loop on the right is leaving the magnetic field. So it's a sheet of copper. Just from the random motion of electrons, you get currents flowing in this metal. So when you pull the metal through here, this loop here, for example, it's leaving the magnetic field. So it has a changing magnetic flux. It experiences a force. So the force turns out to be, like if you're pulling it to the right, current is flowing through this kind of pretend loop. I mean, it's a piece of metal, so it's not a distinct wire, but you could think of it as a loop going around there. So when you pull it to the right, the force is going to be back to the left just because of the direction of the induced current. Copper's not magnetic by itself. It's the fact that, like, you can't take a magnet and pick up a piece of copper. But as you pull the copper through this magnetic field, changing flux, you get currents to flow. A current in a magnetic field experiences a force, and then you have this magnetic braking idea. Okay, good. So that's the basis for magnetic braking. So some semis and things like that have magnetic braking. The thing is, parts wear out a lot less often from this. Like, there's nothing touching, right? You pull this through and you can feel that it's resisting. So you'd have to have this set up somehow on your axles, and nothing really to wear out. Expensive to build initially, but you save money in the long run. Okay, good. So that's a synopsis of what I've said. All right, excellent. All right, good. So in a technique called TMS, transcranial magnetic stimulation, a large oscillating magnetic field is applied to the head via a current-carrying field. The field produces small eddy currents on the brain, inhibiting the neurons in the stimulated area. This technique can be used to determine the importance of stimulated regions in certain perceptions or tasks. Okay, so it's kind of a way of sort of reading what's going on with the brain, actually. So you're stimulating different parts of the brain with eddy currents. And usually after people have this done, they're, in whatever reason, a good mood. I think it stimulates parts of the brain that you don't usually use. Okay. And it might look something like this. Okay. Good. So I'll leave it to you you can look up plenty of different TMS videos, but here's one. Okay. Actually, let's actually watch this video, and then we can then we'll work on this last problem.
Welcome. My name is Dr. Daniel Barton. I'm a child, adolescent, and adult psychiatrist and medical director of the Tennessee TMS Center. You're probably here because you're wondering what TMS is. TMS stands for Transcranial Magnetic Stimulation. It's an FDA-approved treatment for depression. It's also being used to successfully treat issues like anxiety, PTSD, and OCD. And research is finding the use of TMS to be beneficial with individuals dealing with substance abuse disorders, as well as with some of the symptoms of pervasive developmental disorders like Asperger's or autism. Let's talk about how TMS works. Our brains help in managing our thoughts by creating pathways that communicate with each other via electrical and chemical messengers. Each type of thought or feeling coincides with particular pathways or roads that these signals travel along. The more our brain practices certain pathways, the better it gets at doing whatever it is that we practice. It's kind of like muscle memory, but for the neurons in our brain. Now let's focus on how this translates in depression. Here's a functional PET scan of a typical brain. These researchers labeled to light up oxygen and glucose, which acts as the fuel for our cells, in order to see what areas of the brain are working. This is an equivalent scan of the brain of someone with depression. By comparison, the typical brain has more activity in certain regions, like the frontal lobe, but most importantly, in the central areas where our limbic system is. The limbic system is the emotional center of our brain. In the individual with depression, you could say that the limbic system is way out of practice. This is demonstrated by the area being darker because it's not using the fuel, glucose, or oxygen. We'll come back to this. Now let's look at how treatment works. In TMS, a magnetic coil is placed over the head and uses an electromagnetic field which provides for enough energy to cause the neurons at the surface of the brain to reach what we call an action potential. This is a fancy way of saying the neurons turn on, and like dominoes, those neurons send messages that cause other neurons to fire, which cause other neurons to fire, and so on and so on. This roadway of neurons reaches deep areas of our brain, specifically the limbic system that we talked about earlier, and practices or works out those known pathways of our brain that are associated with being more happy, being less anxious, and being more relaxed and content. Remember him? Here's where TMS shines as a treatment. While a singular positive thought can practice a particular pathway once, a singular TMS treatment will practice that positive pathway 3,000 to 5,000 times. A typical course of TMS is around 30 sessions and stimulates positive pathways between 100 to 150,000 times. Now, imagine practicing a golf swing, or tennis serve, or a song on the piano 100 to 150,000 times. You'd get pretty good at it. It's just like Mom and Dad said when you were growing up, practice makes perfect. And that's a lot like what the TMS process is. The more your brain practices these positive pathways, the more of an expert your brain gets at feeling happiness and joy, and the less of an expert it gets at feeling depressed. TMS is a non-invasive, simple outpatient procedure. There's no anesthesia, no need for hospital stays. During the procedure, patients can listen to music, watch movies, or chit-chat like normal with family or clinical staff. Patients can drive themselves to our clinic, receive treatment, and then drive themselves back to work, school, or just go about their day as planned. And what about side effects? This is one of the great things about TMS. Because it is a non-systemic focal treatment, TMS doesn't have any of the traditional side effects of psychiatric medications, which have the potential to cause weight gain, sexual dysfunction, decreased sex drive, memory problems.
Okay, so that was the gist of what TMS does. And I guess it's almost magical to me because you can stimulate parts of your brain without cutting into your brain just from having a changing magnetic field. Let's look at this example problem. A coil used to produce a changing magnetic field in TMS device produces a magnetic field that goes from 0 to 2.5. So there's a changing magnetic field. Okay, let me write this down. The initial magnetic field is 0, and we go up to a final magnetic field, which is 2.5 Teslas, in a time 200 microseconds. So the changing magnetic field, that's going to induce an EMF. Suppose the field extends through the entire head. Estimate the size of the brain and calculate the induced EMF in a loop around the outside of a brain. Okay, so for my brain, I'm going to say it's maybe 20 centimeters, the diameter of it. So the radius, I'll go with 10 centimeters, so 0.1 meters. Just kind of a ballpark guess. I guess I could get a ruler out and measure the size of it, but or maybe take some kind of a ruler and put it all the way around my head. But I'm just going to say the radius is this, and have a circular head. I'll assume that too. So I can get the area, pi r squared, right, the area of a circle. So the induced EMF, something's got to change. The area, in this case it's not changing. I'm assuming that the angle between A and B is 0, so the cosine of 0 is 1. So what's actually changing is the magnetic field part. Okay? So you can put all these numbers together. Pi r squared, then the magnitude of the change. So 0 minus 2.5. You can see the use of the absolute value sign. So I had 0 minus 2.5. I didn't write the 0. And then 200 microseconds. Okay, and then you can calculate how much EMF is actually induced. Okay, so either A, B, angle between them has to change. In most of the problems, it seems to be the magnetic field strength changing. Okay, good. Next slide is more examples, which again, I'll make a separate homework video for this.